Welcome to our talk, Interactive Liquid Splash Modeling by User Sketches. My name is Zhili Chen. I'm from ByteDance, and this is a joint research effort made by Guowei and Huamin Wang from the Ohio State University and Jimei from Adobe Research. So our work is about modeling liquid splashes. And the reason we became interested in splashes is because they're so common in the real world. From the kitchen to the bathroom, from someday worth celebration to another day that kind of sucks. We observe liquid splashes almost everywhere and every day. Because liquid splashes are so appealing yet versatile, photographers and artists love to use them for many artistic and commercial products. But capturing them from the real world is not easy. It requires sufficient photography skills, a lot of preparation, and sometimes even post-processing, like this wine heart picture in the middle. On the other hand, geometry modeling of liquid splashes in 3D is a real challenge. The challenge comes from the fact that the shape of a liquid splash is so complicated, and it has many details like capillary waves and ruptured droplets. In fact, we asked several artists to model a liquid splash in an S shape using some existing tools, such as Cinema 4D and ZBrush. And it turned out to be a very time consuming and labor intensive process. So, this experiment inspired us to build a novel, efficient, and high quality system that can hopefully free people from all these labor intensive works, as shown on the left side. The system works as follows. First, a user uses motion controller to draw sketches in a 3D VR environment. Let the sketches and their velocities be the input. The system then runs a CGAN-based synthesizer to generate a scalar field representing the liquid splash and the velocity field representing the underlying flow. After that, the system performs a physics-inspired process to enrich the splash model with fine details. And in the end, we can use the model for display, further editing, or simulation, which is beyond the scope of this paper. In this video, we show that how the user draws sketches and how the system generates the splash models on the fly. The final result is a butterfly, as if it is made of liquid splashes, as you can see over here. So let's talk about our system. The first and foremost question is, what are the sketches representing? In many previous sketch-based modeling works, sketches represent shape contours and shape features. But this representation is not suitable here because splash shapes are complicated and sketching splash details can be just a nightmare. After quite a few failures, we found that it makes more sense for the user to sketch the flows rather than the shapes. Compared with the shapes, the flows are much simpler and easier to sketch as streamlines. For example, in this water crown, we can use small amount of streamlines traced from some seeding point to represent the sketch of the flow. And this is what the users can draw. So once we have the sketch representation ready, our next goal is to build a database by physics-based simulation. Specifically, to set up the simulation, we put a solid obstacle in the middle of the scene, and we shoot a water streamlet towards it. We then capture the liquid splash caused by this impact. We used 3 types of random variables to generate different splash shapes. They are the obstacle size and shape, water jet size, speed and length, and finally the impact location. After we collect those raw shapes, we perform a series of operations to extract the streamlines and to align the data. In the end, we create a database with more than 10,000 splash shapes, and every shape contains 5 to 20 streamlines, as you can see some of them here. Using the data, we can then train our synthesizer by the conditional GAN network. Like other C-GAN networks, our network contains a generator and a discriminator. For those of you who are not familiar with GAN concept, we train the generator to get more and more realistic results, which can hopefully fool the discriminator. Meanwhile, we train the discriminator to distinguish the generative results from the simulation data. The network structure and the training process is very similar to other C-GAN works, so I would like to skip the details here, and you can find them in the paper. What's important here is that we define both input and output in a grid with the same resolution. Currently, we're using 128 cubic, which is the maximum resolution we can use. And there are 4 channels corresponding to the scalar density and the 3D velocity field. So here's the result. We use the same set of streamlines as input, but with different velocities. And you can see how the velocities affect the result. When the velocity is low, the result tends to be sparse and dispersed. And when the velocity is high, the result tends to form thin sheets. This is actually consistent with the real world, since the thin sheets exist only in high speed. Here's another result. On the upper left, we have the original streamlines and the resulting shape. And the other 3 figures are the results after we introduce a new stroke, colored in yellow. So this example shows that the synthesis process is fairly local and consistent, even though we don't enforce the consistency specifically in our system. To evaluate the accuracy of our system, we also compare the results with the simulation ground truth data. And you can see that the generated result is very close to the ground truth. Here's another example. In general, our system can recover the overall shapes quite well, but you can see that, especially from this example, there tends to be some details missing, like those small water drops. It's not in the generative results. To address the missing detail issue, we propose to develop 2 refinement steps as post-process. The first step is based on particles. We initialize a number of random particles around the boundary of the liquid shape, typically around the splashing front. And then we run particle-based fluid simulation to enrich the model with more particles, as if they are water drops. Here's another result of the milk skirt. On the left, we have the result before the refinement. And on the right, we have the result after the refinement. You can see those new particles added as extra details. Here's a comparison of different milk skirt created from different strokes. Besides the particles, we also would like to address the surface detail of the liquid splash, especially those capillary waves caused by surface tension at a small scale. As you can see in this comparison, our immediate result is short of those waves. Therefore, we developed another refinement step based on the acoustic wave model, and our refined result is shown below. Here's the milk crown example before and after the refinement. And here's another example in a heart shape. On the left, we have the result before any refinement. In the middle, we have the result after the particle refinement. And on the right, we have the result after both the particle and wave refinement. A very interesting feature of our model is that the output contains both the shape and the velocity. So we can continue the simulation to animate the model even further over time. In the next animation examples, on the left side, we have the simulation starting from a static pose, while on the right side, it starts with the generated velocity output. And you will see the difference with and without using the generated velocity. And here we have some more animation examples. So in conclusion, we found that Yes, conditional GAN works well for modeling liquid splashes. The result looks pretty good, but we still have a lot of problems. The first problem is we don't have enough randomness in our results. And using the VR controllers to draw the 3D strokes is not really optimal in terms of a fine control. This problem is fundamentally due to the nature of our supervised network and restriction from the VR hardware, but we are also interested in exploring other solutions. Second, there is still a large gap between the reality and the sensitized results, especially in the small details, and we must improve the realism even further. Finally, whether we can or how we generalize our sketch-based technique for other liquid phenomena beyond splash is an interesting problem, and we don't have answers yet. So that concludes my talk. Thank you for listening.